Hello, Professor.
Oh, hello. Hello, how are you?
I'm fine.
So, so now that we are done with all these midterm exams, we can relax a bit and talk about some more number theory. So I want you to talk a bit more about the Riemann zeta function today. And to start in the following way, maybe to go back to the first video on the Riemann zeta function we did. There was Riemann 1 called.
Okay.
And then I sent you links to several YouTube videos, various people. Take half a minute from here, 2 minutes, 5 minutes from there. We put them together.
Okay.
And then we continue from there.
Okay.
And after that, you can share your screen as you did before and type some things.
Okay. Okay.
So maybe let's watch the last 2 minutes so that to refresh our.
Okay.
Just to remind.
In other words, this thing is a product, like a series, when we have infinitely many terms in a series in calculus. Now we have infinitely many factors in a product. So only if I take all those infinitely many factors in the product, then we get a clean one. If I stop after any finite number of steps, I don't get one. I get one plus some other numbers that are not removed. Some numbers that are not divisible by any of these 2, 3, 5, or 7. Okay. So now he concludes that, let's recall what we saw before. What we saw before was that zeta of s tends to infinity as decreases to 1. That's one thing.
We show this by using the harmonic series.
1 plus 1 over 2 to ds plus 1 over 3 to ds plus
what he's writing or what I'm writing on the board is just definition. Right?
Real no complex. And another thing is this infinite product, which is nowadays called Euler product. So zeta of s is equal to the following product. It's 1 over. It's an infinite product over all the primes, p, right, of 1 over 1 minus 1 over p. It's like that. And this is also for all s larger, for any fixed number s larger than 1. This is an infinite product, but the product converges to 1. That's exactly zeta. Why? Because if you recall what we had before I erased, it was zeta multiplied by all these numbers. There was 1. So zeta itself is 1 over this. Okay.
Okay. Can we stop right here?
Yes.
Now I said earlier. Oh, you can. Yeah. Show me, or you can show that screen. I said earlier that there are more primes than squares. And that's what I wanted to show today. Of course, it doesn't make much sense to say it like this because there are infinitely many squares and there are infinitely many primes.
Yes.
But in some sense, the sequence of squares is more sparse than the sequence of primes. And one way to see this is the following. If I look at inverses of squares, and we add all these inverses, so 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 and so on, we saw and we showed before that this is a series that's convergent. So they are sparse enough to converge. If I take, on the other hand, all the positive integers, 1, 2, 3, and so I take inverses, 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. This is divergent.
Yes.
Now, what happens with a sequence of primes? If I take the sum of inverses, is this going to be convergent or divergent? And that's what we want to show today, that it is divergent.
Okay.
So the sum is infinite. So 1 over 2 plus 1 over 3 plus 1 over 5 plus 1 over 7 plus 1 over 11, just this goes beyond any bound that we fix ourselves, while the sum of inverses of squares will not go. In fact, it's less than 2. No matter how many terms we add, it's still less than 2.
Yes.
Now, in order to deal with this, it's difficult to work with a product, with an infinite product. We're more used to working with an infinite sum.
Yes.
Now, in order to transform an infinite product into an infinite sum, we need to take a logarithm.
Logarithm, yes.
But the Riemann zeta function, it's complicated as is, even before we take a logarithm. So not everybody is able to take a log of the Riemann zeta function. We're not able, so we'll ask someone for help. So we'll ask Achilles for help.
Okay.
That's the first link. Can you share the screen? Just a few seconds. All right, so we see. Can you make it big? I can't see. Now,
yes.
This is not Achilles. Achilles is okay. This doesn't look like Achilles. This is Achilles. Just so that we have a definition for Achilles, so we know who we're talking about. You probably can stop it right now.
Okay.
We don't want to see too much of this
Yeah.
bias. So, one thing that we noticed about Achilles is that he's very fast, much faster than the other guy, definitely.
Yes.
That's why they needed to show us this scene in slow motion, so we can we can see what happens. Now, he wasn't just fast; he was invincible.
Yes.
And we can look at this other. Here's some discussion with someone else whose name is Hector. The discussion is not very friendly, but we can watch 20 seconds of this. This is Achilles. Oh, yeah. And probably it's a good place to stop this right here. Okay. So as you know, Achilles is invincible. Why was Achilles invincible? Among other things, remember, he was dropped in this river that makes him invincible, but they hold it, his mother, when he was, hold it by his heel. So that part didn't get wet. So that's the only way you can kill him. You have to shoot an arrow, but exactly through his heel. And that's what happens in this scene. Let's just watch this 10 seconds or so, how they kill him. And look at the yes, you can stop right there. You saw the heel. Yeah, you can go back 2 seconds and you see it.
You want to see the heel?
Piercing his heel, right. Okay. You see?
Yes.
The only way to kill. Now, that's about Achilles, various things about Achilles. Now we have another video about Achilles. This one. Let's watch maybe 2 minutes about it. So this was done, I guess, before Achilles was killed.
The Greek hero Achilles is challenged to a race by an unassuming Tortoise, who claims that he can beat Achilles as long as he is given a head start. Achilles accepts the challenge, knowing that no man could beat him in a race, let alone a slow-moving tortoise. The tortoise is given a head start. The race begins and Achilles bursts forward, making up ground on the slow-moving tortoise. However, by the time that Achilles has made it to the tortoise's starting point, the tortoise has moved forward by 1 meter. By the time Achilles makes up the ground on the new gap, the tortoise has moved again, creating a new but smaller gap. Every time that Achilles reaches the point where the tortoise was, a new, smaller gap has formed as the tortoise continues to plod forward, and so always remains slightly ahead of Achilles. This paradox was created by the ancient Greek philosopher Zeno, who lived 2,500 years ago. The paradox supports the idea that motion is impossible, as to get from point A to point B, one has to travel an infinite amount of steps. Before I reach my destination, I must first travel to its halfway point. Before I can get to the halfway point, I must first travel to its halfway point, and so on and so on. If one has to travel an infinite amount of distances, then the destination is never reached. But clearly, motion is possible, and we know that Achilles would quickly overtake the tortoise. Many solutions to Zeno's paradox have been offered. The standard solution argues that Zeno was wrong to assume that the sum of the distances which Achilles has to run is infinite.
All right,
Half
so
which
let's stop
Achilles
right here.
runs is a linear.
And, yeah, and let's go with the last video to see the point of view of a mathematician on this.
Okay.
Let's maybe we can watch the first 6 minutes or so of
this,
this, but let's start from the beginning.
Yeah, I'll just delete the previous ones so that the computer is
Right.
not-
The previous ones were more interesting, but let's
Okay.
see what he has to say from the beginning.
Okay.
A problem that's not just of interest to mathematicians like myself, but it's also of interest to physicists and philosophers, and it has been for thousands of years. So Zeno was a Greek philosopher. He lived 2,500 years ago, and he came up with a list of paradoxes. There's about 9 of these paradoxes. The ones I want to talk about, though, are kind of similar. The first one, though, I love because there's a nice little story with it. So the first one is called Achilles and the Tortoise. You've got Achilles and the tortoise in a race. Now the tortoise is slower, of course, so he's given a head start. He's got a 100-meter head start, and then they start the race. Now Achilles sprints 100 meters, and he catches up to where the tortoise was. But in that time, the tortoise has moved on. He's moved on 10 meters. So Achilles now has to sprint to catch up with the tortoise again. So he sprints another 10 meters and he catches up to where the tortoise was. Now, since that time, the tortoise has moved on another meter. So Achilles has to sprint to catch up to where the tortoise was. And this keeps happening over and over again. So the paradox is, does Achilles ever catch up with the tortoise? And that's insane. And obviously, he must do. We all live in the real world. He must catch up with the tortoise. Another of these paradoxes is basically the same, but it's a bit simpler. I'm holding my hands apart like that. Now, I'm going to keep my left hand still. I'm going to move my right hand towards my left hand so that they clap. Now, when I do that, you can think of it like I'm half in the distance, and then half the distance again, and then half the distance again, and again, and again, and again. And then half the distance an infinite number of times, infinitely many times. So does that mean that my hands never clap? Is there some sort of force field here stopping my hands meeting? Well, obviously they do. This is the paradox. So what's going on here? How can an infinite process end? What's going on? And this is part of Zeno's paradoxes. I want to give you the mathematician's point of view for this because, well, some say that the mathematicians have sorted this out. Let's say I start with my hands 2 meters apart, and then I'm going to join them together. So they start 2 meters apart, and then I halve the distance. So I've traveled 1 meter, and then half the distance again. So it now travels another half a meter. Then you do that again, you halve the distance again. So now your hands have traveled a quarter of a meter. And then it's an eighth, a 16th, and 1/32. And then you keep doing this forever, halving the distance forever. Let's say this does have a value. Let's give it a value. Let's call it S for sum. Here's a trick that you can do. first of all, I'm going to multiply by a half. I'm going to multiply the whole thing by 1/2. So if I multiply the left-hand side by a half, you get half of s. On the right-hand side, I'm going to multiply term by term by a half. So 1 multiplied by a half is a half. Actually, I'm just going to write that there. I'm going to leave a little gap. Now I'm going to multiply the half by a half, which gives me a quarter. And I'm doing it term by term. So a quarter times a half is an eighth. And an eighth by a half is 16th. Now I'm going to subtract those two things. If I subtract, on the left, I get s minus a half s, which gives you a half s. On the right-hand side, I'm going to subtract these two lines. So I've got 1, and I've got plus a half minus a half, plus a quarter minus a quarter, plus an eighth minus an eighth. And all the terms cancel out. So all you're left with is 1. Which means, if everything's cancelled out then, you can work out what s is. S is equal to 2. So this would be 2 meters. So your hands would travel 2 meters. Even though it's an infinite process, your hands do travel 2 meters. Now, time is important as well. If each step was taking a second, then that's an infinite number of seconds. Or if it was longer than a second. So you would complete your 2 meters, but it kind of takes an infinite amount of time to complete your 2 meters. So time is important as well. So let's say, we'll do it a little bit faster than that. Let's say I move a meter per second. So I'm going to move a meter per second. It's the same working out. If I half the distance, that would take me 1 second. And then I half the distance again would take me half a second, then a quarter of a second. So I could travel 2 meters in 2 seconds, and my hands would clap. So something like this, an infinite sum, behaves well when if you take the sum and then you keep adding 1 term at a time. So you've got lots of different sums getting closer and closer to your answer. Right? If that's the case, if your partial sums, that's what they're called, they're getting closer and closer to a value, then we say that's a well-behaved sum. And at infinity, it is equal to it exactly. And it's not just getting closer and closer, but not quite reaching. It is actually the whole thing properly.
Okay, let's start. And maybe now we can share your screen and maybe you can type some things. So let's try and generalize this.
Okay. So we start typing?
Yes. So it's a nice idea that he showed.
Yeah.
But we don't have to work just with the number 1/2. Let's take a general number, x, and repeat the procedure.
Okay. So let me just...
Right. Here or another page, doesn't matter.
Okay.
So let's now capital S again. The following sum. So we replace 1/2 by x. So we started with 1. So it's 1 plus, it was 1 plus a half plus a quarter in this case. 1 plus x. Now instead of 1/4, I have x squared. X squared, not x/2, but x squared plus x cubed plus and so on. X to the 4 and so on. So now we have, but we don't stop at an n, but we say plus ... Infinitely many terms. Try and see. Right. With finite many terms, we probably did this before in class.
Yes.
But that's what happens. If we have infinitely many terms like this. Now, if I take x to be 1/2, I get 1 plus 1/2 plus 1/4 plus 1/8. And so on. So we get his series.
Yes.
And the sum of the series was 2 in this case. S equals 2. If we take x to be 1, then that's bad luck. We cannot add these things. Or we can write it like this, 1, yes, because it's 1 plus 1 plus 1 plus 1 plus 1 and so on. So that would be a divergent series.
Yes.
And of course, if I take x to be a number that's even larger than 1, the sum will be, again, infinite. It's a divergent series. Diverges even faster. But if I take any x less than 1, so now I have to be a bit careful. When I say x less than 1, I also have to be clear if my x was positive or negative. Let's say x is between -1 and 1. -1 strictly less than x, strictly less than 1, or in other words, x in absolute value. So the absolute value of x is less than 1. But let's write it like this. -1 less than x less than 1, s converges. Now, just think about what happens if I take s to be -2. It will not converge because it will be 1 -2 plus 4 -8 plus. You see, it doesn't converge to anything. Okay, it will oscillate. Good. It converges, but it converges to what? We want to apply his trick. His trick was that he took his sum s and he multiplied by 1/2. In our case, let's multiply by x. So let's write another line. X times s.
If it is -1, it will convert.
No, not -1. Oh, if it is -1, it's still oscillating. It's 1 -1, 1 -1, 1 -1. It doesn't converge to a specific value.
Okay. So let's do. Okay. Sorry. Yes.
So x is strictly between -1 and 1.
Okay.
Now, we compute x times s because, okay, we see that s converges. These terms are become extremely small. And but that's not what I want. What I want is exactly the value of the sum.
Yes.
In general, in the particular case when x was equal to 1/2, he obtained that the total sum is 2. I want to see what the total sum is in general. So I multiply by x as he did, and I have the following. I multiply this equals. So each of these numbers is multiplied by x. So 1 times s is x, so it's just x. Plus, and now it's x times x is x squared plus x cubed plus, and so on. So exactly as in his case, we get those numbers. In his case, he had 1/2, 1/4, and so on. So let's do the same thing that he did. Let's subtract. S minus x times s is equal to, and now we see that it's exactly 1, because we have an x, but we subtract an x. We have an x squared, we subtract an x squared, and so on. So now we solve for s. We take s as a common factor there, so it's s times 1 minus x equals 1. So we solve for s, and we get s is 1 over 1 minus s. 1 over 1 minus x. 1 minus x.
Yes.
That's a minus, not a plus, right? Yeah.
Yes, it's a minus.
Okay. P. That's it. Now let's see particular cases. In particular, let's say when x equals 1/2, we get s is 2 because it's 1 over. Let's just check. 1 over 1 minus 1/2. In the denominator, I have 1 minus 1/2 is 1/2. So 1 divided by 1/2, it's 2. Now let's take another particular case, which was from this cartoon, from Achilles and the turtle. When x is 1 over 10, x is 1 over 10, let's first write what s was defined, and then we compute it by our formula. S, right, but not this, the first line on the page. Plus 1 over 10 plus 1 over 100 plus 1 over 1,000 and so on, plus ... Actually, let's write this using digits, like the decimal expansion of this. S was 1 plus 0.1 plus 0.01 plus 0.0, right, plus and so on. So in fact, it's 1.11111. So if we do this as we learn in school, what fraction? No, don't do it by our formula, but don't do it how we learned in school. It's a 1, and I think that 0.11111 is, isn't that like 1 over 9?
Yes.
Yeah. But I have a, yes. Please write 1 plus 1 over 9 and then 10 over 9, so it's clear. 1 plus 1 over 9. Because the 1 I have in front, and then the rest of the thing, 0.11111, and so on, is 1 over 9. So it's 10 over 9. Let's double check with our formula that we obtained. We obtained that S was equal to 1 over 1 minus X on another line. So this equals, when X is 1 over 10. All right, let's write what it is. 1 minus 1 over 10 instead of X. 1 minus 1 over 10. And this is 1 divided by 9 over 10. Yeah, the 9 over 10 is in the denominator. We put in a parenthesis, so this whole thing is 10 over 9. You see, it changes. Okay, so far so good. Now we need to do something else. Let's write, maybe on another page. Sorry, so then we don't, or a bit further away. Okay, so let's write this identity that we found. The identity that we found is the following. Let's write on another line, the identity. It's 1 plus 1, okay, 1 plus x not. 1 plus x squared over 2 plus dot, 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 x cubed plus dot, 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 in many terms. This equals 1 over 1 minus x. It goes without saying that this is still for all x between minus 1 and 1.
Yeah.
Now, if I look at both sides, the left side and the right side, I see these are functions of x now, defined on my interval minus 1, 1. Now, let's see. If we recall from calculus. Maybe first calculus class, can we find a function whose derivative is the left side? Well, that would be easy, because I look at 1 and I think about, a function whose derivative is 1. It's x plus. Now, a function whose derivative is x. It's x divided by 2. Right. This whole thing divided by 2 plus. Now, whose derivative is x squared? It's x cubed, the whole thing divided by 3, plus, maybe you can write one more term. One more term. Plus, the next one is x to the 4 over 4, plus dot, dot, dot. Let's write equal. And now let's think. You recall from calculus how you find the function, or whose function, which function has this 1 over 1 minus x as its derivative. Maybe a function whose derivative is just 1 over x. You recall that? Maybe we write ln for the natural log. So it will be ln x, but ln x, the derivative of the natural log of x is, it's going to be 1 over x. I want it to be 1 over 1 minus x. So that's why I take the derivative of natural log of 1 minus x. You put a minus, so you know the chain rule. Good. So this means that when we take the derivative of natural log of 1 minus x, the derivative of log is 1 over that thing. So it's 1 over 1 minus x, and times by the chain rule, the derivative of what's inside. So the derivative 1 minus x, which gives me another minus. So that's why I totally agree with you. It's minus natural log of 1 minus x. Now, let's pause for a few seconds to think about this. Another thing we learn in calculus, if we have two functions and they have the same derivative, it doesn't mean that the functions are the same.
Yes.
You recall, because you can have two functions and they differ by a constant. So a function and a function plus 5.
Yeah.
Right? And they have the same derivative. So it was incorrect for us to write what we wrote above. What we have is that the left side, which is x plus dot, 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 plus, plus a constant is equal to our minus natural log of 1 minus x. But I want to find a constant. So let's remove this x and x plus 5. That was just an example. The two different functions have the same derivative. And let's write in words. To find the constant c, take a particular case for x. Take x equals 0. X equals 0. So we look at both sides. So now on the left side, we get c plus just 0 plus 0 plus 0. All these terms are 0 because it's x squared, x cubed, and so on. All of them are 0. It's 0. Equals what happens on the right side is minus natural log of 1. But what is natural log of 1? 0. So c equals 0. That's the conclusion. Okay. So then, now that we know that c equals 0, we can write the same line again without the c. Okay. And then we have this identity. We can use this in both ways. One way is if we have in a problem this series like that looks like powers of the same number, x squared, x cubed, and so on, and then divided by natural numbers in this order. On the right side gives us the exact evaluation of that. For instance, let's take now okay, let's take x to be 1, not 1. 1, if, okay, yeah, 1 is fine. What happens on the left side? 1, how do you know it's infinity? It's 1 plus 1 over 2 plus 1 over 3. No. 1 over 2.
Oh, you mean this series? Okay.
Yes. Plus 1 over 3 plus, I agree with you, it's still infinity, it's still divergent, because this is the harmonic series. And now this equals, it was minus natural log of, now it's 0. And indeed, you see, natural log 0 undefined, but when x approaches 0, it goes to minus infinity, and with a minus in front plus infinity. So you see, it's consistent. In fact, we were not allowed to just take x equals 1, because our identity was in holds for all x's in the strict open interval from -1 to 1. So I can take numbers that are strictly larger than -1 and strictly less than 1. Now, what happens when I let x approach -1? At -1, it does have a value. And let's see, I just take directly x equals -1. And then what do I have on the left side? Something interesting. 1 minus, right. Yes, this is minus natural log of 2. And this is also equal to, let's see, I take -1, so it's -1 plus, because I want to write it as a series, plus, because this -1 squared is +1. +1 over 2 is -1 over 3, minus none over 8, -1 over 3, x being -1. So it's the signs alternate, and so on. So now if we multiply the whole thing by -1, let's write the equality again. 1, but not equal to this. This is a new line, because I multiply this by -1, the line. It's just not equal to the previous thing. Right. So let's write just one other line. Multiply by -1 and get this form. So it's 1 minus 1 half plus 1 over 3 minus 1 over 4 and so on. It's an interesting series. And this equals natural log of 2 with plus, just ln2. It's a nice evaluation for this alternating series. So it's a series of terms. See, the terms go to 0. But if I add them in absolute value, if I take 1 plus a half plus a third plus 1/4 and so on, I get plus infinity. The series is divergent. But if I take them out with alternating sign like this, This is convergence, so-called alternating series. It converges and converges to exactly natural log 2. A nice evaluation. All right. Now, this is if I take some particular values. Now, let's take another particular value. Let x equals 1 over p to the s. P to the s, comma, where, let's say, where p is a prime and s is just a real number, s is strictly larger than 1. Larger than 1. Now, first of all, am I allowed to take such a value? You see, p is a prime, so p is larger than 1. It could be 2 or 3 or 5 and so on. P to the s is larger than p. So we can note this. 1 over p to the s is strictly less than 1 over p. Let's write it somewhere so then we keep this in mind. 1 over p to the s is strictly less than 1 over p. And this is strictly less than 1. 1 is not a prime. P first prime is p equals 2. So we are allowed to take this. Now, what do we get when I take this? I get the following. Let's write the following: minus natural log of 1 minus 1 over p to the s. P to the s. This whole thing equals, and now it's 1 over, it was x, which is 1 over p to the s, plus the next one is 1 over, in a parenthesis, is 2 times p to the 2s. Let's write this 2 times inside this parenthesis, and then we times p to the 2s. Yeah, and you can close both. Let's see that that's what it is. Because it was x squared, but x squared, if x is 1 over p to the s, x squared is 1 over p to the 2s. But I have an x squared and I have to divide by 2. So that's what we get. And let's write just one more term. Plus 1 over, and then it's 3 times p to the 3s. P to the 3s plus da, da, da. So it gets complicated. However, let's observe one thing. When I take a number like, but let's not write anything. When I took x to be 1/2, I got that the sum was 2. There was a 1 and then a 1/2 and then 1 over 4, 1 over 8. Then when we took x to be smaller, like 1 over 10, the series, this geometric series, converged much faster. It was 1 over 10, and then 1 over 100, 1 over 1,000. So 1 over 10, it's smaller than 1 over 2. True. But it's much larger than 1 over 100. By a larger factor than what 1 over 10, 1 over 2 was compared to 1 over 4.
Yes.
So 1 over 4 was like 1 over 2, but divided by 2. Well, 1 over 100 was 1 over 10 divided by 10. So the larger the number, the smaller the number x is, the bigger x is compared, the smaller x is. But the bigger it is compared to x squared. Or the smaller x squared is compared to x. And x cubed is much smaller than x squared. And x to the 4 is much smaller than x cubed. So this means that for small x, and we can say this in words, so then we don't complicate this. Of course, we're going to do this in the fall, say, semester when we teach this 5C1 class, and we talk about the Riemann Zeta function in more detail. Who's interested to, and everybody in our classes who's still here is invited. We'll do this more properly. But it's enough for us today to just say the following. for small x, minus log of 1 minus x, yeah, let's write it like this, minus ln of 1 minus x is close to, let's write in words, is close to x. Let's look above and see what it was, because it was actually equal to, you see, it's the natural, where is it? Yes, is the third line on this page. X plus x squared over 2 plus da 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 is equal to, yeah, that's the one that you highlighted. If I want perfect equality, I would have to write all these terms on the left side. But as I said, as we noticed, when x is very small, these other terms are negligible compared to x. So our minus natural log of 1 minus x is actually close to x. Okay, in the sense, again, that all the other terms are much smaller than x itself.
Yes.
Good. Now, let's add all this, or let's say the following. In words, let us add this approximation. We work with the approximation. Let us add this approximations, say, if you want, for all prime numbers p, all prime numbers p, where x is as before, where you saying words, where x is as before, x is 1 over p to the s. Yes, that was our x. All right. So now what we get is the following. On the left side, we have a sum. Yes, on the left side first. Okay. That's right. Before you write, we have these logarithms. But now I take all the logarithms. What is my first prime? P equals 2. So let's put P equals 2 and let's write it like this. It's minus, so it's minus log of 1 minus not divided, 1 minus 1 over 2 to the s.
Sorry.
Because that was the first prime. 1 over 2 to the s. Remove P and put a 2 instead of, no, P squared, 2 to the s. Yes.
Yes.
The next one, so minus, because all of them come with a minus, is ln of 1 minus 1 over 3 to the s. Then minus, guess what's the next one? Not 4 to the s, just primes. I take 5 to the s. Let's put one more so then it's visible. What happens? Minus, not, what's the next prime? Minus 7 to the s. And then minus, infinitely many terms. And now we say in words, is close to, now we have to take the sum of those values. Each logarithm was close to x. So before you write anything, the first logarithm was close to x, but x was just 1 over 2 to the s. The next logarithm was close to 1 over 3 to the s. The next logarithm was close to 1 over 5 to the s. So let's add all these things. So the whole sum is close to, and now we say just 1 over 2 to the s, 1 over 2 to the s, plus, okay, word with plus, 1 over 3 to the s, plus 1 over 5 to the s, and so on, plus, Okay. One more thing and we are done. Let us observe that the sum that we said on the left side, we have this sum of logarithms. Observe, let's write in words. Observe that the sum of the logarithms above, we don't just say the words logarithms above, sum of these logarithms above is exactly natural log ln of zeta of s. And you write the words zeta. Yeah, okay, if you want z for zeta, it's fine. zeta of s. Period. Oh, in order to see this, we need to look back at that screen where I was talking, the other me was talking before on the other screen, when we have the infinite product.
Yes.
Do you still have that? And then we
Yeah.
come back here,
I do.
just to double check. So now we see that we finally got our natural log of zeta, but let's see that we have. If you can share the screen. Not Achilles, not the.
Yes, yes.
It was Riemann 2, one of the last screens that we had.
Riemann
Any
1.
screen that has Riemann 1, not Riemann 2. Sorry, Riemann 1. If you still have access to it, last minute, if you can, the larger screen. Right, towards the end where we have. Okay, yeah. Can you make it a bit larger?
Yes.
Yes, and let's wait a few more seconds to. Okay, stop right there. Right, okay, please stop. No. I'm in the way. Please move myself. Move me. Okay.
Yeah.
Okay. I don't know why I was standing there, but okay. So let's talk. What I wrote before was zeta of s equals this product. Okay. So if I take the natural log of zeta, is the natural log of this product. Now this is an infinite product, so the natural log of this infinite product is the sum of the logarithms of the factors. Now let's observe one more thing. Each one has a numerator that's 1, and it's 1 divided by something. But when you take a logarithm of 1 over something, that's exactly minus log of that something. So that's exactly what we had in our sum. It's minus log of the denominator. Let's see what denominator I you cannot see because of my right hand, but it's written P prime. Okay. It's okay. Let's start right. So I said I have to take the product over all primes. The first prime is P equals 2. So I have 1 over 1 minus 1 over 2 to the s. The next prime is P equals 3. It's 1 over 1 minus 1 over 3 to the s. The next prime is 5 and so on. For 5, I get 1 over 1 minus 1 over 5 to the s. So when I take the logarithms, if you imagine what happens, I have logarithm of each of these factors. I have a minus in front of each one because they appear in the denominator.
Yes.
And other than that, I have exactly the logarithms I wanted, because this is natural log of 1 minus 1 over 3 to the s, log of 1 minus 1 over 5 to the s, and so on and so on. So we can go back to the other screen and conclude that indeed the sum of those logarithms is exactly, there's no approximation here, the sum of the logarithms is exactly log of zeta, where I have an approximation, not an exact formula, is in this sum. So we concluded the following. Natural log of zeta of s of zeta of s is close to 1 over 2 to the s, just the sum, because it was equal to the sum of the logarithms that, sorry, the sum of this 1 over 2 to the s plus. Okay. Last thing. Let's recall that we proved, and it was written on the board there, that let us recall that, we say in words, let us recall that as decreases to 1, little less, lowercase, as decreases to 1, as tends to 1 from the right, in the sense that as is larger than 1 but decreases to 1. Remember, zeta of s, z of s, as you put it, z of s tends to infinity, writing words, tends to infinity. We show this by using the harmonic series.
Okay.
Now, if z of s tends to infinity, the logarithm of this thing also tends to infinity at a slow rate. But if a quantity tends to infinity, the logarithm, its logarithm will also tend to infinity. So let's write, thus, log of zeta of s, not log in general, log of zeta of s, let's put a z, ln of zeta of s tends to infinity as decreases to 1, or as approaches 1 from the right. Okay. Thus, now our sum. Okay. Okay. Yes. We. Thus, let's remove z of 1.
Okay.
Thus, remove z of 1, but let's leave this. Let's remove the entirely, because this was not zeta of s. It was close to a natural log of s. And
Okay. Yes.
yeah. Let's remove that. Then let's just put the sum. Thus, 1 over 2 to the s. Because this was close to the natural log. The natural log, we saw that it approaches infinity, tends to infinity. So our sum that was close to the natural log now approaches infinity. Plus 1 over 5 to the s plus, so blah, blah, blah. Approaches infinity. You see, stop right here before you say anything.
Yes.
Okay, you wrote it already. Okay, good. For a fixed s larger than 1, the sum is finite. It's convergent.
Yes.
Even if we have infinitely many terms. Yes. But then this full sum, infinitely many terms, s is, depends on s. But if I take not someone's trying to call, doesn't matter right now. We are close to finishing this.
Yes.
So for any fixed s, this sum of infinitely many terms is convergent, but
yes.
It depends on s. The value depends on s. But then when s decreases to 1, that sum
approaches
the series as a function of s will tend to infinity.
Yes.
Okay. Now let's observe one more thing and we are done. Recall that we wrote that earlier that 1 over 2 to the s. Recall 1 over 2 to the s. 1 over 2 to the s is strictly less than 1 over 2.
Yes.
Was strictly less than 1 over 2. Let's write under this thing. The same with 3. 1 over 3 to the s. 1 over 3 to the s is less than 1 over 3. 1 over 5 to the s is less than 1 over 5. And so on. So now we add all these inequalities. Not only these 3, but for all the primes.
Yes.
For all primes. And we get the following. That our sum that is on the first row on this page, 1 over 2 to the s plus 1 over 3 to the s plus 1 over 5 to the s and so on, is strictly less than, let's write a few terms, 1 over 2 plus 1 over 3 plus 1 over 5 plus a clean thing, has nothing to do with any s. This series is a very clean series. The sum of inverses of primes. The series has to be divergent. Has to be divergent, and that's divergent, anti. Or has to diverge, yes. This series on the right has to diverge, because if this was convergent, say it converges to 10, then everything on the left side is less than 10. Or if the sum 1 over 2 plus 1 over 3 plus 1 over 5 and so on is a bounded sum less than 1,000,000, it means that for all this s, the sum on the left of this inequality is going to be less than 1,000,000. So it cannot approach infinity, which is what we proved before.
Yes.
So that was the contradiction. So the series diverge. So in this sense, we have more primes than squares, in the sense that the sum of inverses of primes is divergent, as we just proved, as opposed to, let's say, the sum of inverses of squares, or sum of inverses of cubes, and all these are convergent. So we can start this video right now. Thank you very much. How long